Welcome in .core. For over a century, quantum mechanics and Einstein's relativity haven't played nice. Now, Aalto University researchers Mikko Paatinen and Jukka Toki propose a bold fix, reframing gravity with the same gauge theory principles behind the other forces. If it works, it could reshape how we understand the universe from black holes to the Big Bang. Keep watching this video to explore more about this topic. The discovery or event at the core of Paatinen and Toki's work is to recast gravity as a gauge theory. Gauge theories rely on symmetries to define interactions and form the foundation of the standard model which successfully explains electromagnetism and the strong and weak nuclear forces. Extending these principles to gravity offers a path to unify it with the other forces. Einstein's general relativity treats gravity as a curvature of space-time caused by mass and energy, a geometric view that has passed every test for over a century. But it struggles in extreme conditions where quantum effects dominate, such as near black holes or at the start of the universe. By reframing gravity as a gauge field, Paatinen and Toki provide a language compatible with its mechanics. Their model introduces four compact U1 gauge symmetries, expanding the mathematical framework to recover our familiar four-dimensional spatium as part of a larger structure. This method allows them to describe gravity as a quantum field while still matching predictions of general relativity at scales we can currently observe. A key challenge in quantizing gravity has always been dealing with infinities that arise in calculations. To address this, the researchers applied renormalization, a tool used in this field of theory to produce consistent finite results. So far, they've shown that their model is renormalizable at one-loop order, an important early step in proving mathematical consistency. What's exciting about this theory? It makes testable predictions. It matches general relativity on known effects, but adds subtle differences in how light bends under strong gravity, signals future lensing surveys or gravitational wave detectors could confirm or refute. Scientific significance and theories. Why does this matter so much? Because it aims at one of science's most important goals, a unified theory that explains all fundamental forces under one framework. Currently, quantum field theory describes three of the four forces, electromagnetism and the strong and weak nuclear forces, with astonishing accuracy. General relativity governs the fourth, gravity, on cosmic scales. But these two worlds don't interact cleanly. When combined, their equations fail, creating paradoxes that limit our understanding of phenomena where both effects are strong, such as the interiors of black holes or the instant of the Big Bang. Paatinen and Toki's approach offers a bridge. By describing gravity with gauge theory, they align it mathematically with the standard model forces, moving us closer to a single framework that works across all scales. This could open the way to addressing questions like what happened at the universe's beginning? How do black holes store and process information? Does space-time itself have a quantum structure? The implications extend beyond theory. Technologies like GPS already rely on relativity. More accurate models of gravity could refine such systems and even inspire innovations we can't yet imagine. Another strength of this model is its falsifiability. It doesn't just speculate, it makes measurable predictions. Future observational data from space telescopes or gravitational wave experiments could confirm whether these deviations from Einstein's equations exist. That said, the work is still at an early stage. While the model has passed key tests showing consistency at one-loop order and reproducing known gravitational effects, its behavior at higher levels of complexity remains unproven. The researchers acknowledge this and invite further analysis, reflecting the iterative nature of scientific progress. Implications and what's next. The most immediate step is testing its predictions. The model forecasts measurable deviation from Einstein's equations, particularly in how light bends under strong gravity. Upcoming gravitational lensing surveys and gravitational wave detectors could provide the high-precision data needed to evaluate these claims. If these differences are observed, it would offer strong evidence that gravity does indeed follow principles. In the laboratory, progress is also underway. At MIT, researchers are preparing experiments using laser-cooled torsional oscillators, instruments sensitive enough to detect the faintest gravitational effects. By cooling them to near absolute zero, they can isolate subtle quantum behaviors in gravitational interactions, providing a complementary test of theories like Paatinen and Toki's. If validated, this framework could influence many areas of physics. In cosmology, it could provide new insights into dark matter, dark energy, and the universe's earliest moments. In astrophysics, it could help explain the behavior of neutron stars and the interiors of black holes. In particle physics, it could lay the groundwork for incorporating gravity into the Standard Model, moving closer to a unified description of all forces. Even if refinements are needed, this work has value. It challenges a traditional purely geometric view of gravity and encourages researchers to explore new mathematical tools for understanding it. It also strengthened collaboration between theorists and experimentalists, helping bridge the gap between abstract models and empirical data. Next comes refining the math, improving the framework, and planning observations to test it. Whether this model holds or inspires the next, it's a real step towards solving one of physics' biggest mysteries, quantum gravity. Outro Parton and Tolkie's model reimagines gravity using the same principles as other forces, a bold step toward unifying physics. Upcoming experiments will test if it holds, potentially reshaping how we understand the universe. Want more breakthroughs like this? Subscribe for updates on the frontiers of science. Thanks for watching Dark Core.